So our next talk is about science. I was thinking of something funny to say, but actually I can only read it. Computational models to predict when diseases turn epidemic. So Eugenio came in from LA, not LA, France, and he's gonna talk about science. So, a big round of applause. Aha, okay. We forgot something. Okay.
Test? Yeah.
Works.
So probably super comfortable, but okay. Yeah, so hi everyone. I'm really excited to be here. And first of all, I really want to thank the organizers for inviting me to speak at this amazing conference. I would like to take you to the amazing world of infectious diseases, which, in a very unscientific way, I like to classify in 4 groups. The first one is like zombie-like diseases that usually they get a lot of attention from the media, and these are Hollywood-style pandemics like the swine flu, SARS. I don't want to downplay them. They represent a real threat, and for example, the Spanish flu back in 1918 killed more people than World War I and maybe World War II. But on a daily basis, people get killed by diseases of class 2, which usually, we're so used to them that we don't talk about them, but in low-income countries, people die of pneumonia, diarrhea, HIV, malaria, and stuff. And even if you remember the Ebola outbreak in West Africa in 2014, 2016, it got a lot of attention, but at the same time, malaria was killing 100 times more people than Ebola. The third class is what I consider threats, even for we in developed countries in the near future. The most important threat is going to be represented by multi-resistant bacteria, so bacteria that can't be killed by any antibiotic. And then some comebacks due to the reduced perception of risk by people. So people are stopping getting vaccines, people are stopping using protections, and so we're getting back like chickenpox, whooping cough, and some sexually transmitted disease. And the last class is even more overlooked, but it is of utmost importance because it can cripple the economy, especially in developing countries, which is diseases that affect livestock and crops. Now, I argue that for all these classes of diseases, we need computational models that even before doing field work, before doing clinical works, or even instead of, we can run these models in our computers and be able to answer these kind of questions. So, for example, if I have a population that's susceptible to a specific pathogen, what happens if the pathogen gets introduced in the population? If I have an ongoing outbreak, can I predict the number of cases next week, next month? And this, like, for example, people did that with the Ebola outbreak. If I want to avoid an outbreak, who should I pay close attention to? Where should I try to detect the disease? Whom should I vaccinate to avoid the disease altogether? And for example, if there is an endemic disease, where should I stockpile my drugs in order to reduce its burden? Now, I think that at this point, this is what you're thinking. I'll get to that. Because, well, I'm no developer. I studied physics, and then I got a PhD in epidemiology. Still, if I look at my working directory, well, this is what it looks like. Of course, that doesn't make me an expert, as more as being able to speak a language makes me a linguist. And indeed, like, if I say we scientists, we code all the time. I basically do everything in Python. Most of my colleagues do. But there is a reluctance to scale up the level of your coding. Basically, most scientists, they learn a few tricks, they repeat them every day to get their algorithms done in a code that nobody will ever see, producing an output that nobody will ever see, except then when you publish and you do some cosmetics on it. But in my case, at least, that doesn't work. Because ever since I started working in this field, well, I had to work in close proximity with people that had very little computational background. And especially since it's infectious diseases, you want to work with people who actually see the patients, so veterinarians, physicians and stuff, and policymakers, public health officials. And if you want to make your job relevant, you have to convince them that your modeling approach is useful in the real world. You have to convince them that you're able to give them answers that they couldn't get with traditional methods. And in order to do that, you have to answer relevant questions from the public health point of view. And to know which questions are relevant, you have to work with them. So it's a loop. You have to convince them to work with you, but at the same time, you need them to be able to produce relevant work that then convinces them. And I think that like the solution out of this loop is to involve them in the modeling process, in the scientific process, to provide them with a framework that they can directly run. They can put the quantitative parameterization for their diseases and their populations and get quantitative predictions themselves. But before delving deeper into this concept, I would like to tell you a little bit more exactly what I do, because I think it's relevant at this point. So let's go back to the first question that I put on my slide. So like, what happens when you have a susceptible population and the case 0 emerges? So for some reason, one person is now infected by a pathogen that wasn't previously there. Well, you have two options about what's going to happen. Either case 0 is not able to infect enough people to sustain the disease, and so the disease quickly dies out of the population. And the population, at the end, it's naive. If you look, for example, for seroprevalence, for the presence of antibody to that disease, you won't find none. On the other hand, if case 0 is able to infect some other people, and then these people infect other people, at the beginning you will have an exponential increase that will lead to an epidemic outbreak. Now, in terms of modeling, what you do, because you want to answer these questions, like what's going to happen, it's going to happen this or this before it actually happens. You want to do it with your modeling. And in order to do that, typically, like the approach that we use is representing the population in terms of a network. So nodes are the hosts for the pathogen, let's say people. Let's say if the study population is people who are attending PyCon Belgrade, the nodes is us. And then links are the contacts through which the particular disease can spread. And of course, these are disease dependent, because if we are talking about an airborne disease like flu or the cold, then even speaking face to face at less than 1 or 2 meters is a contact that's relevant for the spread of this disease. If we were talking about a sexually transmitted infection, of course, we would need to acquire a different kind of data. In terms of the disease itself, well, you represent it simply in terms of a dynamical process in which the nodes are in one of different states. So in this simple example, they are susceptible. They get the disease from a contact, so they become infectious. While they are infectious, they can infect people, and at some point, they will recover. Now, this very simple model, it's still meaningful for some class of diseases, but of course, you might want to add other features like the presence of a latency period, so the time it passes from when you get the infection to when you are actually infectious, or the presence of an immunity. When you recover, you are immune for a disease, sometimes lifelong, sometimes the immunity wanes off after a while. Still, this is like the broad theoretical framework that we use for our models. And to go back to the answer of the case scenario analysis, the way to quantitatively translate this is in terms of what we call R0, which is a fundamental quantity in epidemiology, and it's simply the number of cases, the number of secondary cases generated by a primary case. So clearly, it's intuitively like if R0 is larger than 1, you will have an epidemic outbreak because you will have an exponential increase in the number of cases because I infectious generate more than 1 infectious. On the other hand, if I'm not able even to replicate myself, then the disease will die out. And the disease parameters for which R0 is exactly 1 is called the epidemic threshold because it discriminates between these two qualitative behaviors. So basically, like the working pipeline that we do is like you develop a new theory in terms of a model that can adapt it to a specific disease in a specific context. Then you build a you build a computational implementation of this model that takes real-world contact data as an input, the data that are relevant for the spread of that particular disease. The disease model itself, also in terms of the parameters like the transmission probability upon contacts, the recovery rate, whatever you need to put in your disease model, and this will give you an estimate of R0 or the conditions that, like the threshold conditions that discriminate between the two regimes. And that's exactly what I did. So on one hand, we developed like the theory for computing these particular epidemic thresholds for a generic network of contacts that involves in times at the same time as the disease spreads. And then we implemented it in terms of a library that you can download, and you can compute the epidemic thresholds given your data, given your disease, without needing to understand this. And it's especially relevant because we don't, like a public health official doesn't have to understand physics or mathematics, doesn't need to, and if it's required, then it's going to ignore the whole thing because it says, yeah, this is like some physician's masturbation, and I don't care about it. So let's talk about a very specific example so that maybe I'm clearer. This is an amazing data set collected by some people that basically went through a prostitute rating forum in Brazil, and looking at the posts, they inferred sexual contacts between female sex workers and their male clients. And of course, like this is a very special data set because, to my knowledge, it's the only data set recording sexual contacts that doesn't rely on self-reporting, which is known to be biased. And of course, it's relevant to study the spread of many sexually transmitted infections, like, for example, syphilis. So what you do is basically you prepare your contact data set in terms of a very simple text file in which you have like every row is a contact, and you have the ID of the sex worker, the ID of the client, and the day in which the contact occurred. You feed it to a class that basically handles this time-evolving network and allows for some basic network manipulation. And this class will be the input of another class that actually implements the numerical algorithm for threshold computation. And to that class, you were also feeding the parameters of the disease. So for example, in the case of syphilis, basically syphilis at the primary stage can be cured by a single shot of antibiotics. What you want to put inside is like, imagine that you are monitoring this population and you are testing people for syphilis positivity on a regular basis. And in a test and treat scenario, if you find a positive, you can treat it right away with a shot of penicillin. So you can play around with the testing rate of the two classes of the population. So maybe you can monitor better sex workers than clients. You put all that and you get your numbers. I don't want to get inside the details because that's not the point. But the cool thing is that like you can make interesting studies. Like for example, here we played around the average infection period, which is basically the average time it takes to be cured, and the estimated latency period of syphilis, which is not very known. It varies a lot, and what we showed that like different estimates of the latency period combined with the interplay of the testing period can increase the risk of the population as a whole or decrease it. And like when I'm talking about the risk of a population, I'm not talking about the risk of a specific person getting a disease, but again, scenario analysis, what's the likelihood that syphilis is going to be endemically present in that population. Now, the cool thing about this data is that you can download them. Of course, they are anonymized, but they are publicly available. It's not the case for many data sets that are very relevant for infectious diseases. So for example, mobile phone data, where people make calls or send SMS. This is an amazing tool for studying classes of infectious diseases. Worldwide human mobility networks, and for livestock diseases, livestock trade networks. All these three data sets, they're very restricted, both for privacy reasons, of course, and because of their huge commercial value. Let's focus on livestock, for example. Basically, the whole European Union collects amazing data on livestock movements because following, I don't know if you're familiar with the foot and mouth disease. It's a very contagious livestock disease. There was a huge outbreak in 2001 in the UK that basically resulted in a loss of billions of pounds. So after that, the whole European Union got scared and started tracking everything possible in the livestock market. So what actually you can do if you access this data is build this kind of network in which you have all the premises involved in cattle market in a country, farms, slaughterhouses, whatever. And each day of the year, you know, like if farm A sells cattle to farms B, you can translate it in terms of a directed link that's weighted by the number of animals that are sold. And you can track, if you want, you can really track these animals individually. As I said, the European Union takes this thing very seriously, as this interesting story that got the news a couple of months ago of this cow, this Bulgarian cow, that wandered off alone and crossed the border with Serbia. And that was okay, but then she decided to go back home, so it entered the European Union illegally, and she was sentenced to be slaughtered. But of course, like when you have relevant issues, people get committed, and so we managed to save the cow, which probably now it's even eaten by the owner, but everybody was happy that at that point she wasn't killed for being an illegal immigrant. Anyway, those data exist, but they're far from being free to access. So the idea was, okay, instead of going for the data in each specific country of the European Union, let's build a huge partnership with people that in their own country, they already have access to those data, either because they are the veterinary institutions in charge of collecting the data for that country, or because they are research institutions that are already using those data for research. So through that, we got access to 14 datasets comprising 12 European EU countries plus Switzerland, which means 75% of the EU market, which means 65 million animals. So cool dataset, but again, I, like myself and the people I work with, we couldn't have direct access to those data. So I have a question. I didn't. How are you evaluating R0 if the network is not observable? Some statistics of the networks. Okay, I'll answer that later. So the idea was like, okay, so we build a library for standardized livestock network analysis, which like provided some analysis tool that we deemed interesting and relevant for these particular networks and the diseases that we were studied. Every partner in their own country would run the analysis library locally and then give us back a standardized output with which we perform the comparative analysis that then fed back to the community for interpretation. So the cool thing is that it requires no data sharing and it's completely scalable to an arbitrary number of countries, data set, even beyond the European Union, as long as you have this particular data. Basically, it works, I mean, it's very simple. So you have a class that you feed with your own network that it's formatted in a very simple way. This class also performs what we might call like basic network manipulation, because you have like this network of livestock has a daily resolution, but for some analyses, for example, you might need to aggregate data, so like this class does that, but the user, typically maybe an epidemiologist or veterinarian, doesn't need to care about it, because then once you load like your data into this class instance, then you have a set of functions that take your network as an input and then do some pieces of analysis that we want. So for example, you have a function to study the geography of your market. Here you have on your left-hand side, you have the density of active premises across Europe. On the right-hand side, you have the fluxes of cattle, so if there are some geographic places in which you have a net inflow or outflow of cattle. Alongside a spatial analysis, you can perform a temporal analysis in which here, for example, you have the number of active premises daily in each country. And even eyeballing this time series, you can make out different, for example, seasonal patterns. But of course, you have tools to analyze this time series, for example, in terms of the spectral properties, so that then you can like extract some features from every country and then compare them. Then you have other tools to perform some more advanced network analysis, because like the spatial and the time analysis were clearly at a macroscopic level. We also wanted to see how the network at the microscopic level, so in terms of who is in contact with whom, changes in time. So for example, let's say that you have, I don't know, the situation of the market in Germany in January 2018, and you ask the question, what remains of that market if you look at 2 months later? How is, like, can you define a memory for the network and see how it changes? You can do that. In the end, when you have all these analyses and others, you can extract some features and then try to classify countries and years within each country in terms of these features. For example, here I plotted all the countries and the years using dimensionality reduction, and you see like some interesting and expected things like Switzerland, Austria, and Slovenia clustering together. Other expected things, Northern Ireland stands in the middle between Great Britain and Ireland, and something that, I mean, it's totally unexpected, and the fact that Spain and Hungary apparently share a lot of the features in terms of, the dynamics of cattle market. The last question was, okay, how do we use that for our purposes, which is study the risk at which these markets are if an introduction of a very contagious disease like foot and mouth were to occur. To do that, we had to integrate this analysis library into the first library that I shown you. And this, so that we could build a predictive model that basically said, okay, given some features of a market, can I predict its vulnerability class? So can I see if it's more at risk or less at risk? So the answer was, yes, you can do that, and you can do it with even with 5 selected features. And this is good for us because maybe what we are working on is imagine that you have a country outside the European Union for which you don't have all this data, but maybe you have some coarse grain data. We want to see if it's enough to predict its risk, and then to highlight which features particularly drive it. So maybe you can design interventions aimed at changing the market in a way that its risk reduces. But from my point of view, this has been a huge computational challenge. It really put my programming capabilities to the limit, and honestly, I don't really like what I did in the sense that the final step is really something that sort of works, but I don't think it's stable. I don't know. It's simply the very limit what I could do, and for that, I think because ideally I would like to live in this world where, as a modeler, I interact with the public health official to develop a theory that can answer relevant questions, and then I work with the developer to actually build a computational framework that then the public health official can directly use. However, I never work in this world, I always work in this world. And the problem is that, it's always more or less going to be this way. There have been, in my field, some people who really spent a lot of time and effort in developing something that can even be used as a game in which you set your own disease and you let it spread around the world. But I'm not talking about showcasing. I'm talking about, for every project, doing it on a daily basis. And the problem with science is that you can't do this on a regular basis for 2 reasons. Firstly, because in science you have a pressure to publish. Every effort that's not aimed at publishing is discouraged, simply because if you don't publish, you don't have a career. Secondly, because there is no money to bring in a consultancy or hire some developers, because basically scientists go around begging for money for projects, and so, yeah, money is tight. So I would like to finish, and then I'll be happy to answer the questions, with a very vague perspective, which is there, and it's mostly a question to you, because I have no answer, I don't, maybe even the question yet, is there any possibility to devise a meta something that can be like a framework that every modeler can already put their model inside, and you already have something that makes it sort of accessible to non-technical people, so to public health officials, that they can run it, they can do stuff without either me trying to do something that I wasn't trained to do, or the unrealistic scenario of having a complete team on every project. That's it for my presentation. I'll be happy to go through the questions. Do you have any experience with cellular automata in disease spreading modeling? And can you give us a brief comparison between CA and temporal networks models? No, I don't. I don't have a particular. Who asked the question?
Okay. Who asked the? Oh, okay.
Maybe if you can, like, explain me a little bit. Probably I can answer more.
Yeah, it's a
easily.
general approach with the several automata to modeling, spreading, or some information diffusion.
Okay. And how does it work in brief?
We can after
Okay,
talk,
okay.
yeah, discuss. Yeah.
How are you evaluating R0 if the network is not observable, but only some statistics of the networks? Okay, actually, it's even easier because from a theoretical point of view, you have two approaches for dealing with like these dynamical processes on networks. One is you have a specific network structure, like I told you. It might evolve in time, but you know exactly who's in contact with whom at any moment in time. And you use some theoretical approaches which in general are pretty difficult. On the other hand, if you know just some statistical properties of the network, so you know, for example, the average number of connections that every person has, or maybe you know also some degree correlations and stuff like that, then basically from a theoretical point of view, it's strange, like, because who asked this question? Because I'm looking at somewhere, but I don't know. I would like to look at someone. No. Anyway, conceptually what you do is instead of computing your quantities on a specific network that has these properties and then averaging, you average over all the possible networks that respect these statistical properties, and you get a formula out of this averaging process, which is called annealing. But again, I don't want to get too technical. Maybe, like, if the person is interested, we can talk for hours on that. So it's even easier. That's what I want to say. What are Python-specific tools and libraries you are using for analysis and visualization in your research? So, yeah, I should have mentioned that. NumPy, SciPy, Pandas, NetworkX, which is I don't know if you're familiar with it. It's a library for network analysis. It's very convenient, but it's very slow, so it works for smallish networks. Then what? Scikit-Learn, and I think that's pretty much it. Why do you use in Python and not some other languages like MATLAB, R? So I don't use MATLAB because I'm a physicist, and mathematicians use MATLAB. No, I'm joking. It's a bit like a part serendipity, and a part is that when I started using Python, I really didn't feel the need to use anything else because it's elegant, it's sort of easy to learn at the beginning, but then, I don't know, I wouldn't use anything else. And every time people trying to convince me to try something else, like even R, I can do some things in R, but honestly, even looking at an R script makes me want to go back to Python. So I don't know, I'm sorry I don't have a very technical answer. It's simply, I think everybody is using Python more and more. I think it's gonna replace everything, even in science. I still use C++ for some stochastic simulations that require optimization. So when you're really doing something like, I have my population and I have to sample a probability of a specific node infecting another node and stuff like that, I still use it in C++. I don't know, I like people try to convince me to use Julia, but I don't know what, maybe if you know better than me, I still think that doesn't have that many libraries. So yeah, I stick to my 95% Python and 5% C++ for the moment. Do you know of other examples in other academic fields that are doing similar things to overcome data availability issues? Also, how do you ensure accurate use of the library? Do you have any error detection features or offer training? Okay, so yes, the first part of the question, yes, it's basically it's a problem and it's challenged everywhere in what we could call complex systems and complex networks, because like I told you about applying these things to infectious diseases, but there are a lot of people who apply similar techniques, similar methodologies inherited from statistical mechanics, mathematics, computer science to other fields like sociology, neurosciences, mobility networks. You mentioned it. So absolutely, it's shared, and there's a data need in every of these fields, and sometimes even the networks are the same, because some mobility networks are used to optimize traffic, but can also be used to study the spread of diseases. So I think more and more, like this idea of bringing code to data rather than the opposite is gaining ground, and I'm sure that, I mean, probably you are more expert than me in this field, but like, for example, we are starting to work with Orange, the mobile phone company, for some mobile phone data in Africa, and that's, I mean, they're super sensitive, of course, about this data, and so you have exactly this. So they provide you with the algorithm that you have to run on their data, and this is the only thing that you can do. There was a second part of this question, who was about the library, providing training and error. Okay, so the first part, how do you ensure the correct use of the library? I don't, because honestly, I don't know how to do it. That's the main, like, that's why I'm here. I have no idea. This is like a poor man's attempt. I put a lot of effort in it. I enjoyed it. I learned a lot of things, but I'm not claiming that this is anything like professional level. So it's basically on good faith of who uses them, and like they can talk to me, but there's no standardized machinery put in place to do that. Training, I haven't done it for the moment, again, because it's something that takes a huge amount of time. But, for example, for this mobile phone project that I talked about, because now I'm working with HIV in sub-Saharan Africa, and especially in Botswana. So if we do manage to get this data, then part of the project is going there and provide computational training to actually, like, not to naive people, because people that already have some computational trainings, but train them on network modeling and handling this kind of data, and like compute this kind of simulations. So again, it's something that I think it's very important. As I said, in research, if you're not publishing, you're dead. So all of these things always get low priority, and I think that this is a shame, but I mean, I'm not here to talk about the problem of research. How long does it take to compute one simulation? What infrastructure are you using? It depends. So if we are talking about this kind of, like, for example, the scenario analysis that I showed you in the beginning, this is basically computing the spectrum of a big matrix, which is too big to compute directly. So basically, since it's a product of matrices, you keep multiplying sparse matrices against a vector until you convert, like the vector converges to the principal eigenvector of the matrix. It's pretty, like you can do it on a laptop for a network of 50,000 nodes. Like, yeah, I would say that pretty much a limit for a laptop. And then you would need to go to to a cluster or something. Again, big deal about that, because that's another problem that I had. You're giving this library to people that have no idea how to use it, have no idea what they really can do with the data. So there was one person who, the data couldn't leave a specific room, and she had just a desktop computer on it. So I said, well, okay, let's leave it there to run, I don't know, until it burns down, because we couldn't put it on a server. Sometimes, like, this is a mess, because like in academia, sometimes I just paid for Amazon services out of pocket, because I was so frustrated that nobody was providing me some infrastructure. If you're lucky and you apply to a project, then you can get some good machines, but I don't know. It's bad.
Okay. If there's no more questions, Eugenio, thank you very much for the talk.
Thank you.
I'm Eugenio Valdano. I'm an infectious disease modeler at the University of California, Los Angeles. I just finished my talk here on using computational models to predict and forecast the spread of diseases in human and animal populations. I'm really happy that I'm here. I was really grateful to the organizers for inviting me, because it's giving me a chance to connect with people that could offer me real help on like framing my science into some tools that then can be used by people who are non-expert, or maybe they are expert in other fields, or policymakers, so to convince them that our models are useful and to get feedback from them. So I'm enjoying the conference, I'm learning a lot of things, and yeah, just happy to be here.